Welcome, everyone. Today, we're tackling something that really affects all of us. This super complex connection between global climate change, the air we breathe, and ultimately, our health.
Yeah, it's a big one. We've been looking at this scientific chapter that digs into, well, the history of it all and where things might be headed.
Exactly. And our mission today is basically to pull out the key stuff, the most critical insights, and make sense of how these huge environmental issues, climate and air quality, are really linked.
And what that means for you, for your well-being, it's crucial.
So let's maybe start with the history. How did we even get here?
Right. So historically, if you look at developed countries, the focus was really on, local air pollution, the stuff you could see and smell.
Like smog in cities.
Yeah, exactly. And regulations, cleaner tech, they definitely made a dent in that visible stuff in many places, no question.
Okay.
But, and here's the chapter highlights, the progress we've made on those pollutants. It might actually be getting undermined by greenhouse gases, the very things causing climate change.
So they're not separate problems at all.
Not really. They're tangled up together, deeply interconnected.
Okay, so let's unpack that historical side a bit more. You mentioned visible stuff, like back in the Industrial Revolution.
Precisely. Mid-1800s, you start burning tons of coal. And what comes out? Smoke, soot, sulfur dioxide, nitrogen dioxide. A real cocktail.
Nasty stuff.
Yeah, and the immediate effects were obvious, right? Breathing problems you could barely see across the street in some industrial towns. Very localized, though, affecting the immediate area.
Okay, that makes sense. Industrial smog. But then things changed with cars, didn't they?
Big time. The car era brought us something new. Photochemical smog. This is different. It's not just direct soot.
Right, it involves sunlight.
Exactly. Nitrogen oxides, VOCs, volatile organic compounds, basically chemicals that evaporate easily. They react in sunlight.
And VOCs come from cars, but also other things.
Oh yeah, industry, solvents, even vegetation sometimes. But cars were a major new source. And this smog wasn't just local smoke anymore. It covered, whole regions sometimes.
And the danger wasn't always clear at first, was it? I'm thinking of that London smog event, 1952.
Oh, that was a wake-up call. A terrible one. Just a few days of intense smog, and the estimates are like 4,000 people died.
Wow, 4,000.
It just hammered home how deadly concentrated air pollution could be.
Yeah.
Really shifted the understanding of air quality and its direct health impact. A sobering moment.
Definitely. And then there's acid rain. I always think of that as, an 80s problem, but it started earlier.
It did, yeah. It's fascinating. The effects on rain were noticed way back in the mid-1800s in Britain, near industrial areas.
The way.
Yeah. But by the mid-20th century, it was a much bigger issue. Northern Europe, North America, affecting lakes, forests, buildings. Another step up in scale, from local smoke to regional acid rain.
So the problem kept spreading out, and then you get pollutants that travel even further, transboundary stuff.
Right. That brings us to POPs, persistent organic pollutants. The key word is persistent. They stick around.
Like pesticides,
Yeah.
DDT and things.
Exactly. Things like aldrin, chlordane, DDT, and industrial chemicals too, like PCBs, dioxins. They don't break down easily.
Okay.
And worse, they build up in fatty tissues. They move up the food chain. Biomagnification.
Right. And the chapter mentioned them ending up in the Arctic, affecting indigenous people there. That's pretty shocking.
It really is. It shows the global reach. Stuff used thousands of miles away ends up concentrating at the poles. They call it the grasshopper effect.
Grasshopper effects.
Yeah, chemicals evaporate in warmer places, travel in the atmosphere, then condense and deposit when it gets cold. They sort of hop towards the poles.
Wow. So our actions here really do have consequences everywhere.
Absolutely. It's a stark picture. What we do in industrialized areas impacts the most remote places, and the health of people living there. It really makes you think.
Okay, so that's the journey, historically.
Yeah.
Where are we now? You said there's been some progress on those older pollutants?
Yeah, in places like the U.S., the Clean Air Act was huge. It set up these national standards, NAAQS, for the main criteria pollutants.
Those are the ones like carbon monoxide, lead, ozone, particulates.
Right. SO2, NO2 as well, the ones known to be harmful.
And the data shows it worked, to some extent, even with more cars and a bigger economy.
It did. If you look at the trends since 1970, like in figure 13.1 in the chapter, you see vehicle miles traveled way up, GDP way up, but the total emissions of those criteria pollutants actually went down.
That's kind of amazing, actually, how...
Technology, mostly. The big one was the catalytic converter for cars, massively reduced hydrocarbons, CONO and ONDX, really cleaned up tailpipes for those specific things.
Which definitely helped air quality in cities.
No doubt. Huge benefit. But There's always a but, isn't there?
Uh-oh, what's the twist?
Well, those catalytic converters, while cutting down those other pollutants, they accidentally produce something else, nitrous oxide, N2O.
And N2O is bad.
It's a greenhouse gas, a really potent one, much more warming potential than CO2, molecule for molecule.
Oh, so solving one problem sort of contributed to another.
Kind of, yeah. It highlights how these things are linked, and solutions can have unintended side effects. It's not always straightforward.
A classic environmental trade-off.
Exactly. And this really brings us to the core issue the chapter emphasizes: fossil fuels. Burning them is the common link.
Right. Source of both the air pollutants and the greenhouse gases.
Absolutely. Look at table 13.2. It lays it out. Fossil fuel combustion gives you CO2, methane, N2O, the climate changers, but also NOx, SO2, particulates, ozone precursors, even air toxics like benzene, all from the same source.
So common sense says cutting fossil fuels should be a win-win. Clean air and fighting climate change. Co-benefits.
That's the idea, yeah. Clear short-term air quality benefits. But the chapter also suggests the long-term health picture, considering climate change itself, is, well, more complex.
How so? What does climate change do to air pollution?
This is where it gets really interesting, kind of a feedback loop. Climate change isn't just happening alongside air pollution, it's starting to influence it.
Okay, explain that. The chapter mentions ozone and acid rain specifically.
Right. These are secondary pollutants they form in the atmosphere, and weather is key to their formation.
And climate change messes with the weather.
Exactly. Take ozone smog, basically. It forms from those NOx and VOCs reacting, but it needs sunlight and heat to really get going.
So warmer temperatures is more ozone. I think figure 13.2 showed that link pretty clearly for New York and Detroit.
Precisely. Higher temps speed up the chemical reactions, and think about weather patterns. Climate change might mean more of those stagnant, high-pressure systems in summer.
Perfect conditions for ozone to build up. Lots of sun, still air.
Yep, and then you have local topography, like in LA or Mexico City, trapping the pollutants, making it even worse.
And ozone's not just annoying, it's bad for your lungs.
Definitely. It irritates your respiratory system, can reduce lung function, makes things like asthma worse, increases susceptibility to infections, and there's concern about long-term chronic effects, too.
Okay, what about acid rain? How does climate change play into that?
Well, acid rain forms when SO2 and NOx react with water vapor. A warmer atmosphere can hold more water vapor.
Wow, potentially more fuel for the reaction.
Potentially, yeah. Plus, changes in rainfall patterns, how often affect how the acid gets deposited, whether it's wet rain or dry particles. This impacts ecosystems. And remember, SO2 itself is a health concern. Think back to that London smog.
So climate change can act like an amplifier for existing pollution problems.
That's a good way to put it. It can exacerbate things. And there are other ways, too.
Like what?
Well, the urban heat island effect.
Yes.
Cities are already warmer, right? Add climate change warming on top, and that extra heat can really drive up ozone production locally.
More smog in cities.
Could be. Then there are changes in wind patterns, cloud cover, how often the air stagnates versus gets cleared out. It all affects how pollutants build up or disperse. It gets complicated and maybe less predictable.
And the chapter mentioned plants releasing more VOCs when it's hotter.
Yeah, another feedback. Trees and plants naturally release some VOCs. Higher temperatures can increase those emissions.
And VOCs are ingredients for ozone.
Exactly. So warming could lead to more natural precursors for smog.
It's like a chain reaction.
Sort of. And beyond the chemistry, think about climate variability. More extremes. Heat waves. Droughts.
Which means more risk of wildfires.
Huge one. Wildfire smoke is packed with particulate matter and other nasty stuff. We saw how bad respiratory problems got during the big El Niño droughts in 97-98 because of fire smoke. Climate change is projected to increase fire risk in many regions.
That directly impacts air quality over massive areas.
For sure. And it's not just smoke. Think about allergies.
Oh, yeah. How does climate fit in there?
Well, changing temperatures and rainfall can affect when plants release pollen, how much they release, maybe even how allergenic it is. Could mean longer or more intense allergy seasons for lots of people.
Yeah. Okay, this is a lot of interconnected threads. And it feels like human health is caught right in the middle. Especially this idea of heat and pollution hitting us at the same time.
That's a major concern. We know heat waves themselves are dangerous, increasing mortality, especially for vulnerable people.
Right.
But there's evidence for synergistic effects, meaning the combined effect of heat stress and high air pollution, like ozone or SO2, can be worse than just adding the two effects together.
So 1 + 1 = more than 2, health-wise.
Potentially, yes. Your body's already stressed by the heat, then your lungs get hit with ozone. The combined assault might overwhelm your system more easily. Some studies, like from Athens or Belgium, suggest this happens.
That's pretty sobering. These threats can amplify each other.
And the chapter has that figure, 13.3, which tries to map out all these pathways.
Right, the one showing how climate change, rising temps, weird water cycles, sea level rise leads to all these downstream threats.
Exactly. It connects the dots to impacts on air quality, heat stress, food and water issues, natural disasters, even infectious disease patterns.
Because temperature and rainfall affect insects and microbes.
Precisely. And things like contaminated water after floods, forced migration, economic impacts, it all circles back to public health. It even touches on how climate change can affect the stratospheric ozone layer, which impacts the UV radiation reaching us.
So it's this huge cascade of effects, all starting from those core changes in the climate system, driven largely by
Fossil fuels primarily,
Yeah.
which also directly cause a lot of the air pollution. It's all linked.
Okay, so wrapping this up, the big takeaway seems to be you absolutely cannot think about air pollution and climate change as separate things.
Definitely not. They're two sides of the same coin in many ways, driven by common sources, and they interact in ways that significantly affect our health.
And while some places have cleaned up some of the traditional air pollution,
Climate change is throwing a wrench in the works, potentially making air quality worse in new ways and amplifying health risks like heat stress. Plus, the burden isn't shared equally. Developing nations often get hit hardest by both.
it really underlines the need for, well, joined-up thinking and more research into these complex interactions.
For sure. We need to understand these connections better to find solutions that actually protect public health effectively.
Absolutely. So maybe a final thought for our listeners. Considering all these tangled links, where do you think the most critical point of action is for protecting public health? Is it tackling emissions, adapting to heat, something else?
That's the big question, isn't it?
Something to definitely mull over. How do these global issues play out right where you live? Thanks for joining us on this deep dive.
Global climate change and air pollution, interactions, and their effects on human health. By Jonathan A. Patz, MD, MPH, and John M. Balbus, MD, MPH. This chapter from Global Climate Change and Air Pollution, Interactions, and Their Effects on Human Health by Patz and Balbus examines the intricate relationship between these two environmental issues and their consequences for human well-being. The authors present a historical overview of air pollution, tracing its evolution from local to regional and global concerns, while highlighting the increasing impact of greenhouse gas emissions. The text discusses various pollutants, including fossil fuel byproducts, ozone, and persistent organic pollutants, detailing their sources, transport, and health ramifications. Furthermore, the chapter explores how climate change exacerbates air pollution through mechanisms like increased temperatures and altered atmospheric conditions, ultimately impacting human health through diverse pathways. What are causes of climate change? Based on the sources, several factors contribute to climate change. One major cause is the increasing levels of greenhouse gas emissions. The atmospheric concentrations of CO2 and other greenhouse gases have been rapidly increasing beyond any conditions observed in the historical record. Fossil fuel combustion is a common source of these emissions, releasing CO2, NO, and other greenhouse gases into the atmosphere. In the United States, emissions of CO2 from fossil fuel combustion grew by 9% between 1990 and 1996. Globally, these greenhouse gases have increased substantially since the mid-1800s due to human activities. The sources highlight that fossil fuels are a major source of both conventional air pollutants and greenhouse gases. The burning of fossil fuels for energy leads to a significant release of greenhouse gases, including CO2, which accounts for 81% of the total U.S. emissions of greenhouse gases in 1996. Furthermore, population growth and increases in energy consumption lead to increased fossil fuel emissions. As populations grow and energy use rises, the demand for burning fossil fuels increases, consequently increasing the emission of greenhouse gases that contribute to climate change. The chapter also discusses how global climate change can exacerbate the impacts of air pollution on human health and the environment, suggesting a close link between the causes and effects of both issues. What are impacts of climate change and air pollution on human health? Based on the sources, both climate change and air pollution have significant impacts on human health, and these impacts can be exacerbated by their interactions. Impacts of climate change on human health. Global climate change may worsen the health impacts caused by the emission of greenhouse gases and conventional air pollutants. Increased temperatures due to climate change can lead to a rise in heat-related illnesses and mortality. A study in U.S. cities projected a 2 to 3 degrees Celsius increase in average summer temperature could lead to a 70 to 150% increase in heat-related mortality. Climate change can increase the frequency and intensity of extreme weather events such as floods and droughts. Flooding can cause drowning, injuries, and increases in infectious diseases like leptospirosis and hantavirus pulmonary syndrome. Droughts can lead to reduced agricultural productivity and contribute to food insecurity and malnutrition. Shortages of water can also impact hygiene and increase the risk of diarrheal diseases. Climate change can affect air quality. Warmer temperatures can increase the formation of ground-level ozone. Climate change can also influence increased frequency and intensity of stagnation periods, which can worsen air pollution. Changes in climate, such as increased temperatures and altered precipitation patterns, can affect the transmission of infectious diseases. For example, warmer temperatures at higher latitudes and altitudes may increase the range and activity of disease-carrying insects like mosquitoes, potentially affecting diseases like malaria. The quality of food may also deteriorate due to increased temperatures, potentially increasing the transmission of foodborne illnesses.
Climate change may exacerbate the health effect of wildfires by contributing to more severe and prolonged fire seasons. Smoke from wildfires contains particulate matter and other pollutants that can cause respiratory and cardiovascular problems. Impacts of air pollution on human health. Exposure to air pollutants can cause a wide range of respiratory problems, such as asthma and emphysema. Air pollution has been linked to increased incidence and severity of asthma in children. Air pollution, including particulate matter PM, ozone, nitrogen dioxide and O2, carbon monoxide, CO, and sulfur dioxide, SO2, can negatively impact the cardiovascular system. Studies have shown associations between air pollution and increased risk of heart attacks, strokes, and other cardiovascular diseases. Ozone can cause symptoms such as irritation of the eyes, nose, and throat, pain when taking a deep breath, coughing, and increased susceptibility to respiratory infections. Long-term exposure to ozone may reduce lung function. Exposure to air pollution has been linked to premature death. Certain air pollutants like lead can have severe health effects, particularly on children, including neurological and developmental problems. While lead levels have decreased significantly due to regulations, historical contamination remains concern. Mercury, emitted from burning fossil fuels and other sources, can bioaccumulate in the food chain and cause neurological damage, especially in developing fetuses and young children. Exposure to acid rain, formed from sulfur dioxide, SO2, and nitrogen oxides, NO, can indirectly impact human health by affecting ecosystems and water quality. Interactions and combined effects. Global climate change can exacerbate the effects of air pollution on human health. For instance, warmer temperatures can increase the formation of ground-level ozone, a major component of smog. Increased frequency of heat waves, combined with elevated levels of air pollutants, can worsen respiratory and cardiovascular conditions and increase mortality. The chapter focuses on the interactions between greenhouse gas emissions and conventional air pollutants and their combined effects on human health and the environment. In summary, both climate change and air pollution pose significant threats to human health through various pathways, and their effects can be interconnected and amplified. Addressing both issues is crucial for protecting public health. What human race can do to minimize the impacts? Based on the sources, there is a focus on understanding the problems and their interactions, but there isn't extensive detail on specific actions the human race can take to minimize the impacts. However, some inferences and related points can be drawn. The sources highlight the increasing levels of greenhouse gas emissions from fossil fuel combustion as a major cause of climate change. Minimizing these emissions at a global level would be crucial in mitigating climate change and its associated health impacts. This could involve transitioning to cleaner energy sources, improving energy efficiency, and reducing overall energy consumption. The sources note that fossil fuels are a common source of both conventional air pollutants and greenhouse gases. Actions to reduce the burning of fossil fuels would therefore have co-benefits in reducing both air pollution and greenhouse gas emissions, thus minimizing the impacts of both on human health. The chapter discusses the importance of understanding the interactions between greenhouse gas emissions and conventional air pollutants and their effects on human health. This suggests that a comprehensive approach to minimizing impacts would need to consider these interactions rather than addressing the issues in isolation. The mention of the Clean Air Act and its revisions in the United States indicates that regulatory measures aimed at controlling air pollutants have been implemented and updated. These regulations, and potentially more stringent ones, could be seen as an ongoing effort to minimize the health impacts of air pollution. The fact that emissions of certain criteria air pollutants have decreased in the U.S. between 1970 and 1997, even with increases in population, vehicle miles traveled, and GDP, suggests that such regulations can be effective. The study projects in the sources that show increases in heat-related mortality with rising temperatures imply that mitigating the extent of temperature increase through reduced greenhouse gas emissions would be essential to minimize these health impacts. While the sources don't provide a detailed list of actions of the human race to minimize impacts, they lay the groundwork for understanding that reducing fossil fuel dependence and implementing effective air quality regulations are key areas where action is needed to address both climate change and air pollution and protect human health. The interconnectedness of these issues suggests that solutions should aim to address them in an integrated manner.
As the 21st century begins, the concern about many local and regional air pollutants has become less acute in the United States, Canada, and other developed nations. The implementation of regulatory measures and the development of cleaner technologies have resulted in the improvement of some indicators of air quality. Many developing countries have a different experience because they have not yet developed or adopted many of the regulatory measures of the industrialized world to reduce the levels of local and regional air pollution. United Nations Environment Programme 1991, World Bank 1997. However, for both developed and developing nations, evidence is growing that global climate changes caused by the emission of greenhouse gases may exacerbate the impacts of air pollution or human health and the environment. See chapters 7 and 8. The focus of this chapter is on the interactions between greenhouse gas emissions and conventional air pollutants and their effects on human health. Ever since the hazards of breathing soot and fumes were recognized midway into the Industrial Revolution, engineers have striven to develop cleaner technologies. Theoretically, the ideal engine, defined in terms of the cleanest byproducts, would emit only carbon dioxide, CO2, and water, neither being directly toxic to humans or the environment. Only recently has CO2 been recognized as an undesirable byproduct through its function as a greenhouse gas. The atmospheric concentrations of CO2 and other greenhouse gases have been rapidly increasing, see Figure 7.11, beyond any conditions observed in the historical record and represent a new environmental challenge. Houghton et al. 1996. This chapter contrasts the ramifications of increases in greenhouse gas emissions against the backdrop of improving trends in conventional air pollution in the United States and Canada. A historical perspective reveals a new dimension of air pollution issues that are more regional and global in scale. This chapter then focuses on pollutants that are dependent on climatic conditions. Climate change may actually make it more difficult to control the formation of some pollutants, such as ozone. Finally, the broad scope of potential health effects of climate change worldwide is briefly reviewed. A historical perspective on air pollution. From local to regional to global. Historically, the developed nations have gone through a series of transitions with respect to air pollution problems. By the mid-1800s, the combustion of fossil fuels had fouled the urban environment in industrial cities. At that time, smoke, soot, particles, sulfur dioxide (SO2), and nitrogen dioxide and O2 were the predominant emissions of concern. These pollutants caused respiratory irritation, hindered visibility, and blackened buildings. Later, the advent of the automobile introduced the problem of increasing concentrations of nitrogen oxides, NO, and volatile organic compounds, VOCs, in the urban environment. As chemical precursors to GRUND-level ozone, these pollutants resulted in a new type of photochemical smog, consisting primarily of ozone whose formation was catalyzed by sunlight. After the 1952 disaster in London, England, where a 4-day period of smog caused an estimated 4,000 deaths, Logan 1953, it became strikingly clear that local accumulations of air pollution were hazardous. The adage, "The solution to pollution is dilution," was fervently followed, leading to the construction of higher smokestacks and the relocation of polluting industries farther away from urban centers. While local air quality benefited from the greater dispersion of pollution afforded by higher smokestacks, problems of regional air pollution, such as acid rain, emerged or were exacerbated. Acid rain demonstrates the shortcomings of addressing pollution from only a local perspective. The regional problem of acid rain was actually first described in the mid-1800s in reference to the effect of industrial emissions on precipitation in the British Midlands. It has long been recognized that acid rain is widespread in Northern Europe and Eastern North America. By the mid-1980s, roughly half of the sulfuric acid rain falling in eastern Canada originated in the United States. Just as much of the Scandinavian acid precipitation has been traced to industrialized areas of Central Europe and the United Kingdom, Schindler 1988. Recent studies have led to discoveries of areas affected by acid rain in the western United States, Japan, China, the former Soviet Union, and South America. Transboundary air pollution. Toxic air pollutants such as persistent organic pollutants, POPs, can travel long distances. POPs include pesticides such as aldrin, chlordane, DDT, dieldrin, heptachlor, and toxaphene. Industrial chemicals like polychlorinated biphenyls, PCBs, and industrial or incineration byproducts such as dioxin and furans. POPs are highly fat-soluble. They degrade very slowly in the environment and can bioaccumulate to high levels as they move up the food chain. For example, dioxin bioaccumulates through terrestrial food webs and can become concentrated in milk and other dairy products. Indigenous people near the Arctic, who rely on fatty foods high on the food chain, such as polar bear, seal, and fish, can receive considerable exposure to POPs, and the placentas of pregnant women in these areas are often found to have high levels of POPs that pose fetal risk. Some POPs can act as endocrine disruptors, mimicking the body's hormones. Estrogenic chemicals, including some organochlorines such as DDT, some PCBs, dioxin, and furans, may be responsible for declining sperm counts and the rising incidence of abnormalities in the human male reproductive tract, Jensen et al. 1995. The transport of POPs can transcend international boundaries, as detailed in a report of the Commission for Environmental Cooperation, CEC, which was established under the North American Free Trade Agreement, CBC 2000. For example, 15 to 25% of the dioxin deposited in Lake Michigan comes from sources as far away as southern Texas. Up to 90% of POPs applied as agricultural pesticides are retained in the atmosphere or are revolatilized. Atmospheric deposition currently contributes the majority of the total yearly input of PCBs to Lake Superior, Environmental Protection Agency, EPA 1996A. POPs eventually concentrate in water, soil, and wildlife in the cooler, northern latitudes because of normal atmospheric convection patterns and the tendency of POPs to revolatilize many times, termed the grasshopper effect. When the chemical is cooled, it condenses and precipitates out of the atmosphere, so that deposition tends to prevail over evaporation at high latitudes. POPs also degrade more slowly at cold temperatures. Polluted air masses from industrial sources have also been tracked across the Atlantic Ocean and the Arctic by documenting unique trace metal content within these air masses, Schindler 1988. In 1998, some air pollution in the northwestern United States was even found to have originated in Asia, a transport process that would generally take 4 to 10 days, Monastersky 1998. Dust clouds from Asia, tracked by satellite in the spring of 1998, deposited detectable levels of arsenic, copper, lead, and zinc at the pristine site of Crater Lake, Oregon. Global warming is the ultimate example of the global effect on air pollution, on a par with the global threat of stratospheric ozone depletion.
The geographic point of emission of greenhouse gases has little relation to the effects of this phenomenon. Aggregated local and regional emissions are having a global impact whose full implications for the world's climate are still being learned. Trends in air pollutants and greenhouse gases. In 1972, under provisions of the U.S. Clean Air Act, the newly established EPA was required to set national ambient air quality standards, NOxs, for current criteria pollutants deemed to be potentially hazardous to human health. The term criteria is an administrative designation by the EPA for carbon monoxide, CO, and O2, particulate matter, PM, SO2, ozone, and lead, PB. The standards covering these pollutants were designed to be protective of the most vulnerable subgroups within the population, such as asthmatics or persons with emphysema. In 1997, EPA revised the original health-based standards for criteria air pollutants to add new standards. For particles that were less than 2.5 microns in diameter, PM2_5. Since 1970, the emissions and concentrations of air pollutants in the United States have decreased substantially despite large increases in total population, vehicle miles traveled, VMT, and gross domestic product, GDP. From 1970 to 1996, the U.S. population increased by 29%, VMT increased by 121%, and the GDP increased by 104%. Yet aggregate emissions of criteria air pollutants decreased by 32%, figure 13.1. Changes in the emissions of individual pollutants range from a 98% decrease for lead to an 11% increase for NO2. Table 13.1 summarizes the percentage changes in national air quality concentrations and emissions. The experience in Canada has been similar. Environment Canada 2000. Nevertheless, direct exposure to air pollution continues to affect human health adversely in the United States and Canada. For example, a recent study of 11 Canadian cities showed an increase of 8% in daily rates of non-traumatic mortality associated with days of high levels of air pollution for NO2, ozone, S02, and CO. Burnett et al. 1998. While emissions of most criteria air pollutants have been decreasing, emissions of CO2 from fossil fuel combustion in the United States grew by 9% between 1990 and 1996, EPA 2000A. Figure 13.L compares trends in the emission of criteria air pollutants, along with population, VMT, and GDP, with trends in the emission of CO2. Thus, as cleaner technologies mandated under the U.S. Clean Air Act have reduced the levels of criteria pollutants, except for NO2 and ozone in some regions, the emissions of greenhouse gases have been relatively unaffected by regulations. In essence, while the United States may be benefiting from cleaner air nationally, the country continues to emit substantial amounts of CO2, exacerbating the problem of global climate change. Figure 13.1 U.S. trends in emissions of criteria air pollutants, emissions of carbon dioxide, and related factors. Emissions of volatile organic compounds, VOCs, are included in the emissions of criteria air pollutants, since tropospheric ozone is created from VOCs rather than emitted directly from a source of ozone. VMT, vehicle miles traveled, GDP, gross domestic product, population, emissions of criteria air pollutants. Source, redrawn from Environmental Protection Agency, 1999A, Executive Summary, page 3, and Mar. Land et al., 1999. The catalytic converter developed for motor vehicles illustrates this paradox of trading one air pollution problem for another. Vehicles now sold in the United States emit 96% less CO, 98% fewer hydrocarbons, and 90% less NOx than vehicles sold in the early 1970s. EPA 1999A. Some of these reductions are the result of catalytic converter technology. As exhaust gases pass over the catalysts, chemical reactions convert pollutants, hydrocarbons, NOx, CO, into harmless gases, CO2, nitrogen, and water. 1. Hydrocarbons combine with oxygen forming CO2. 2. NOx react with CO to produce nitrogen and CO2. And 3. NOx react with hydrogen to produce nitrogen and water vapor. While greatly reducing emissions of CO, NOx, and hydrocarbons, Catalytic converters generate nitrous oxide, N20, a greenhouse gas that is presently unregulated and has 310 times the global warming potential of CO2. See Chapter 7. Combined emissions of greenhouse gases from stationary and mobile sources have increased by 21% from 1990 to 1996, primarily because of rising rates of N20 generation in motor vehicles, EPA 2000A. Cars with catalytic converters emit up to 5 times the N0 of cars without the devices, although the most current generation of converters have somewhat improved. Table 13.1 Long-term change in U.S. national air quality concentration and emissions. Fossil fuels, the common source of air pollutants and greenhouse gases. Fossil fuel combustion is a common source of emissions of CO2 and the 6 criteria air pollutants: CO, N02, PM, S02, ozone, and lead. Table 13.2, EPA 1997. See that also box 13.1. The use of fossil fuels, particularly gasoline, also releases air toxics such as benzene, toluene, and VOCs. EPA 1997. The term air toxic is an administrative designation by the EPA for a variety of air pollutants, largely volatile compounds and heavy metals, that are not designated as criteria air pollutants. Fossil fuel combustion produces nearly all of the C0 released into the atmosphere from human activities. As the most abundant greenhouse gas, CO2 accounts for 81% of the total U.S. emissions of greenhouse gases, equaling 1,788 million metric tons of carbon equivalent, MMTC, 1996. This unit of measure is used because greenhouse gases differ in their global warming potential. Chapter 7. Although greenhouse gases, such as methane, CH4, N20, and chlorofluorocarbons, CFCs, have a greater warming potential than does CO2, the magnitude of its emissions ensures that CO2 contributes the most to enhanced greenhouse warming, and CO2 levels are the focus of many projections of climate change. CO2, CH4, and N20 occur naturally in the atmosphere, but human activities have substantially increased their concentrations. Since the mid-1800s, these greenhouse gases have increased by 30, 145, and 15%, respectively. Houghton et al. 1996. While the burning of fossil fuel is the largest source of CO2, agriculture and decomposition of landfills are important sources of CH4 and N2O. EPA 2000A. Table 13.2 shows trends for all greenhouse gas emissions and sinks, presented in MMTC units. Note the prominence of fossil fuel combustion.
Mercury is an example of an air toxic whose emissions stem from burning fossil fuels, especially in coal-fired power plants. Other sources include waste incinerators, landfills, copper and lead smelting operations, and cement manufacturing plants. Anthropogenic emissions have increased the global atmospheric burden of mercury by 2 to 5-fold, CBC 2000. A major proportion of the mercury present in the atmosphere is elemental mercury, which is extremely volatile and, in its gaseous form, has an estimated atmospheric residence time ranging from 3 months to 2 years. Organic methylmercury can bioaccumulate through the food chain in aquatic systems to reach toxic levels in predatory fish, as was the case in Minamata Bay, Japan, where severe birth defects, e.g., cerebral palsy, resulted from fetotoxicity in pregnant women who consumed contaminated fish, Coos and Longo 1976. While the mercury in Minamata was not airborne in origin, it alerted the world to the dangers of mercury in the environment. Currently, 5 Canadian provinces and over 35 U.S. states have issued health advisories to reduce the consumption of certain freshwater fish that are known to contain excessive levels of mercury. Many co-benefits can be achieved by reducing the emissions of the fossil fuels that are a common source of criteria air pollutants, air toxics, and greenhouse gases. For example, if nations abided by the Kyoto Protocol to reduce their emissions of greenhouse gases, see Chapter 6, what might be the benefits in terms of the effects on human mortality? An interdisciplinary working group examined this question by combining models of energy consumption, carbon emissions, and associated emissions of PM. PM has been linked to increased mortality, Dockery and Pope 1994, Pope et al. 1995, Samet et al. 2000. Even at levels below the NOxes, PM increases daily rates of cardiorespiratory mortality and total mortality in the United States and Europe, Katziani et al. 1993. In children, PM levels also correlate with increased hospital admissions, school absences, and medication use, as well as a reduction in lung function, measured as peak respiratory flow rates, Bascom et al. 1996. Under a climate policy scenario approximating that of the Kyoto Protocol, e.g., the United States emitting 7% below 1990 levels of greenhouse gas emissions, approximately 700,000 premature deaths due to exposure to PM might be averted annually by the year 2020 as compared with the business-as-usual forecast. Working Group on Public Health and Fossil Fuel Combustion, 1997. This analysis showed the potential near-term co-benefits of long-term policies to mitigate global climate change. Climate change and levels of air pollutants. Secondary air pollutants. Fluctuations in weather have the most influence on pollutants that arise from chemical reactions in the atmosphere. These secondary pollutants, such as ozone and acid rain, are derived from a mixture of pollutants directly emitted, which are termed primary pollutants. Even with the improving air quality in the United States and Canada, urban ozone pollution and regional acid rain persist as problems and have the potential to be exacerbated if air temperatures warm. Ozone, as described in Chapter 7, forms secondarily in the lower atmosphere by a temperature and sunlight-dependent reaction between NOx and VOCs, precursors of the formation of ozone. The major source of NOx in North America is fossil fuel combustion used in transportation and electric utilities. Since 1970, the number of vehicle miles traveled in the United States has increased at a faster rate than that of the overall population, see Figure 13.1. From 1970 to 1994, car ownership in Canada rose from 310 to 484 vehicles per 1,000 people, Last et al. 1998. Transportation is also a major source of anthropogenic VOCs. Other sources of VOCs include incinerators, gasoline vapors, paints and solvents, and some trees or other vegetative sources. The influence of weather on ozone formation. Tropospheric ozone, as a photochemical oxidant and the main ingredient of urban smog, is pervasive and difficult to control. The reaction between NOx and VOCs to form ozone is catalyzed by ultraviolet radiation and requires relatively high ambient air temperatures, see Chapter 7. Meteorological factors that could theoretically influence the levels of tropospheric ozone include ultraviolet radiation, air temperature, wind speed, and atmospheric mixing and transport. In general, there is a direct correlation between temperature and levels of ozone, Kamens et al. 1982, Gray et al. 1987, Sampson 1988. Increases in atmospheric temperature accelerate photochemical reaction rates in the atmosphere and tend to increase the rates at which tropospheric ozone and other oxidants, e.g., hydroxyl radicals, are produced, Hatakeyama et al. 1991, Morris et al. 1995. Studies of ambient temperature have reported that successive episodes of high temperatures characterize years with seasonally high levels of ozone. The relationship is nonlinear, and above a temperature of 32 degrees Celsius 90 degrees Fahrenheit, there is a strong correlation between temperature and levels of ozone, Figure 13.2. However, levels of ozone may not always increase with an increase in temperature. For example, the production of ozone is reduced when the ratio of VOCs to NOx is low, see Figure 7.8.
In the eastern United States and in Europe, the majority of days when the levels of ozone exceed air quality standards occur in conjunction with slow-moving high-pressure systems around the time of the summer solstice, National Research Council, NRC 1991. This is the period of greatest sunlight when solar radiation is most intense and air temperatures are high. The relatively high levels of ozone in the United States during 1988 and 1995 were probably due, in part to hot, dry, and stagnant conditions, Patz et al. 2000. During 1995, one of the hottest years on record, 32% of Americans, or 71 million people, resided in counties in which ozone levels exceeded the NMQS's, EPA 1996A. Episodes of high levels of ozone last 3 to 4 days on average and extend over a large area, i.e., greater than 600,000 square kilometers. Figure 13.2 relationship between maximum daily ozone concentration and maximum daily temperature in New York City and Detroit, Michigan. Source: redrawn from Environmental Protection Agency 1996b, Figure 3.9. Several factors associated with high-pressure systems are conducive to the photochemical production of ozone. Large high-pressure systems often create an inversion of the normal temperature profile, trapping pollutants in a shallow boundary layer at the Earth's surface. Winds associated with major high-pressure systems are generally light, allowing greater accumulation of pollutants. Clear, warm conditions generally associated with large high-pressure systems afford ample sunlight to catalyze the photochemical production of ozone, NRC 1991. Conditions in Los Angeles illustrate how the combined characteristics of meteorology and topography can adversely affect the air. This area is dominated by a persistent high-pressure system off the Pacific Ocean. WBKH forms an inversion layer trapping pollutants over the city. Topography, river valleys or regions surrounded by mountains, also provide pockets to trap accumulations of primary pollutants and ozone, often capped by an inversion layer. Because of the region's low latitude and relatively clear skies, plenty of ultraviolet radiation is available for photochemical production of tropospheric ozone. A similar situation occurs in Mexico City, box 13.2. Trends in summer climatic conditions in the United States may have become more suitable for the formation of ground-level ozone. From 1949 to 1995, the number of summer heat waves, defined as more than 3 consecutive days with average apparent temperatures exceeding the 85th percentile, has increased by 20%, according to one study, Gaff N. and Ross 1998. Climatic conditions could become more suitable for ozone formation under projections of global warming, but the extent of ozone formation will also depend on air mass and wind conditions. The influence of weather on ozone transport. Urban smog has long been viewed as a local issue. However, both ozone and its precursors can travel relatively long distances in the atmosphere and be transported from region to region and across international boundaries. Such processes of transboundary pollution transport have implications for distant downwind populations. Analyses by such groups as the Ozone Transport Assessment Group, OTAG, have confirmed that in the eastern United States, some areas experience a considerable influx of ozone across air boundaries and cannot meet air pollution standards by local measures alone, Ginnup and Column 1997. The distance that ozone can be transported ranges from 150 to 500 miles, rough 1Y240 to 800 kilometers. For example, ozone precursors from New York City are transported by prevailing winds on a roughly 200-mile northeast trajectory through Connecticut and as far as northeastern Massachusetts, Cleveland et al. 1976. Consequently, southwestern Connecticut has the highest concentrations of ozone in this region. The mid-Atlantic and northeastern United States are affected by even broader regional ozone transport. While the highest emissions of the ozone precursors, VOCs and NOx, come from large urban metropolitan areas, the largest elevated point source of NOx emissions comes from the industrial Ohio River Valley, Ginnup and Column 1997. Based on spatial patterns and transport considerations, general control measures should clearly target urban non-attainment areas that do not meet NOxes, as they contribute significantly to their own ozone problems. However, with the Ohio River Valley's high density of NOx point sources, NOx controls targeted for this region may be an important measure for effectively reducing ozone pollution for the entire eastern United States. The health effects of ozone. Ozone causes symptoms of respiratory and mucous membrane, eyes, nose, and throat irritation. As a stroric oxidant, ozone can cause both cellular and structural damage in the lung. 3 types of respiratory responses to ozone exposure are 1. Irritative cough, 2. Reduced lung capacity, as well as decreased expiratory flow rates, and 3. Inflammation of the airway lining or submucosa, Bascom et al. 1996. An inflammatory response usually develops within an hour after exposure and persists for up to 24 hours. Exercise, of course, can increase the dose inhaled because of higher ventilation rates, and most vulnerable populations include asthmatic children in the northeastern United States, where daily ozone levels may remain elevated for 6 to 8 hours. Bascom et al. 1996. Epidemiological studies of emergency room and hospital admissions indicate ozone's significant health effect. During the summertime, when many viral respiratory infections have subsided, exposure to ozone contributes an estimated 10 to 20% of all admissions to hospital due to respiratory conditions. On the days with the highest levels of ozone, exposure to ozone can account for nearly half of all respiratory admissions. PA 1996a. Even levels below the NMQSs can cause reversible decrements in respiratory function, including airway constriction, reduced lung volume, irritating cough, and chest pain. Bascom et al. 1996. The effects of chronic exposure to ozone are less well understood. However, an analysis of pulmonary function data from the Second National Health and Nutrition Examination Survey, NANS2, revealed some association between ambient concentrations of ozone and the loss of lung function over time. Schwartz 1989, Some evidence also suggests that increased incidence and severity of asthma are related to exposure to ozone, although it is difficult to separate the effect of exposure to ozone from concomitant exposure to PM. EPA 1996a. In Mexico City, ozone has been linked to increased admissions to hospital for lower respiratory infections and asthma in children. Romeu et al. 1996. Ozone has been implicated in the exacerbation of asthmatic reactions by reducing the amount of allergen required to induce symptoms. Koren and Bromberg 1995, Koren and Utel 1997.
Acid rain. SO2 and NOx oxidize via reactions with hydroxyl radicals and hydrogen peroxide in the atmosphere to form sulfuric acid and nitric acid, respectively. See Chapter 7. Acid deposition can be either wet or dry. Wet deposition occurs when emissions of sulfur oxides, primarily SO2, and nitrogen oxides are transformed into ads in the atmosphere and then fall to Earth as fog, rain, hail, or snow. Dry deposition occurs when these acid aerosols are brought to Earth by gravity or other non-precipitative means. The National Surface Water Survey, which was conducted by the EPA, examined acid-sensitive areas of the United States comprising 1,180 lakes and 4,670 streams. Atmospheric deposition was found to be the dominant source of acid anions in 75% of the acidic lakes and in 47% of the acidic streams. Baker et al. 1991. According to the National Acid Precipitation Assessment Program, NAPAP, sulfur compounds from fossil fuel emissions are major precursors in the acidification of these surface water bodies. NAPAP 1991. In the United States and Canada, coal-fired power plants, oil and gas processing, and the smelting of sulfur-rich ores account for about 2/3 of SO2 emissions, CEC 2000. While global sulfur emissions from fossil fuel combustion are comparable to those from natural sources, over 90% of atmospheric sulfur in northern Europe and eastern North America is anthropogenic in origin. These findings have displaced earlier claims that volcanoes, trees, salt marshes, or other natural sources were primarily responsible for acidification in these regions. Schindler 1988. Although the causes of many regional patterns of acid deposition remain uncertain, several of the factors that affect ozone formation also influence acid deposition. Penner et al. 1989. Higher temperatures accelerate the oxidation rates of SO2 and NOx to sulfuric and nitric acids, further potentiating acid formation. For example, high temperatures accelerate the production and concentration of hydrogen peroxide. This, in turn, increases the oxidation rate of SO2 to sulfuric acid and ultimately the production of acid rain.
The health effects of sulfur dioxide. SO2 is an irritant that can inflame the lining of the respiratory tract and may have been a key component in the smog disaster that killed thousands in London in 1952. In Ontario, Canada, sulfate levels have been found to correlate significantly with relative humidity in the summer. Bates and Sisto 1987. And the concentration of SO2 was a predictor of hospital admissions for respiratory causes in the summer. On days with peak levels of pollution, summertime haze, comprising mostly ozone and acid aerosols, was associated with roughly half of all respiratory admissions. Thurston et al. 1994. These atmospheric chemical reactions are, therefore, essential in understanding the potential risk to health of changing climate conditions, including temperature and humidity. Potential effects of climate change on air pollution in the United States. As population growth and increases in energy consumption lead to increased fossil fuel emissions, the accumulation of CO2, once thought to be a clean and harmless byproduct of combustion, now poses indirect public health and ecological ramifications via global climate change. See possible pathways of the effect of global climate change on public health, below. The change that is likely to have the most effect on conventional air pollutants is an increase in temperature. Warmer temperatures due to climate change, all other things held constant, may increase concentrations of ozone and acid aerosols, as well as emissions of particulates and allergens. See under climate variability, biomass, air quality, and health, forest fires and allergens, below. A rise in temperature could affect concentrations of ozone by modifying the factors that affect the production of ozone, NRC 1991. 1. Elevated temperature ozone formation in the atmosphere is highly dependent on temperature. Urban areas tend to absorb and hold more heat, a process termed the urban heat island effect. The urban heat island effect can drive up air temperatures by 4 to 5 degrees Celsius or more, Landsberg 1981. The urban heat island may significantly contribute to elevation of ozone levels by adding thermal energy that can enhance the chemical formation of ground-level ozone, Quattrocchi et al. 2000. Also, NOx and VOC precursors of ozone are concentrated in congested cities. Urban air quality could therefore be particularly altered by higher global temperatures. 2. Increased frequency and intensity of stagnation periods. Climate change could result in more frequent or intense high-pressure systems, which provide favorable conditions for the reactions that produce ozone in the atmosphere. 3. Increased water vapor concentration. In addition to enhancing the formation of acid aerosols, increases in water vapor can potentiate the formation of ozone, Penner et al. 1989. 4. Increased emissions of precursor pollutants. Forests, shrubs, grasslands, and other sources of natural hydrocarbons, VOCs, emit greater quantities of these compounds at higher temperatures. Soil microbial activity may also increase with warmer temperatures, leading to an increase in NO emissions. On the other hand, factors that could lead to reduced ozone concentration include the following. 1. Increased cloud cover. A more vigorous hydrological cycle due to global warming could lead to an increase in cloudy days. More cloud cover, especially in the morning hours, could diminish reaction rates, thus lowering ozone formation. 2. Increased thickness of the boundary layer of air. Higher temperatures might be associated with greater convection, resulting in reduced atmospheric stability and higher wind speeds. If precursor pollutants, VOCs or NO, are mixed in a greater volume of air, they will be less concentrated and less ozone will be formed, Smith and Turpic 1989. The net effect of these factors is unclear. However, modeling studies combining these variables are being performed to assess the effects of climate change on air quality.